Okay, hello. So this will be my second time recording this because the first time I recorded the whole thing and my microphone was not on. So that's why you should do a mic check. Very useful. Okay, question 1. A cube is given by the region bound between 0 to 1 for x, 0 to 1 for y, and 0 to 1 for z. Has this density function. I'm going to place that with the rho symbol. And we gotta find the x-coordinate for the cube center of mass given this. Okay, so this is a density thing where they already gave us the mass. So remember, if we want to find x bar, since now we have 3 variables, it'll be the moment at yz, which in this case will be the same triple integral. And you can think of it the same way. It's just x multiplied by the density equation, which will now be x, y, and z divided by the mass. Okay, so let's find this. So it'll go from 0 to 1 for all 3 of them. I think I just woke up my roommate. I'm sorry, Brady. And it'll be x times x plus yz dx, dy, dt. So x squared plus x, y, z. We're going to integrate this from 0 to 1 of dx, which will get us x cubed over 3 plus x squared over 2 times yz from 0 to 1, which gets us 1/3 plus 1/2 yz. So now if we integrate from 0 to 1 again, you get 1/3. Oh, sorry, 0 to 1. Darn. Oh, no. Of 1/3 plus 1/2 yz, you get 1/3 y plus 1/4 y squared z from 0 to 1. Simply gets you 1/3 plus 1/4 z. So the last thing is 1/3 plus 1/4 z dz gets you 1/3 z plus, in this case, 1/8 z squared from 0 to 1, which will get you 1/3 plus 1/8, which I believe I can simplify this down to 8/24. Plus 3/24, which gets you 11/24, which is your moment at yz. So to find x bar, we simply put the moment at yz divided by mass, which is 11/24 over 3/4. So you get 11/24 multiplied by 4/3. I'm going to turn this into a 1/6. So you get 11/6 times 3, which is 11/18, which is our answer E. In this case, that is correct. Okay, number 2. A helix curve, which is parameterized by this, cosine t, sine t, and t, bound between 0 and pi/2. So we got to compute this line integral. In this case, since we have a vector r of t but a scalar, the line integral will be f plug in r of t times the magnitude of r prime of t dt. So let's find r prime of t first, which in this case will be negative sine of t, cosine of t, and 1, which means that the magnitude r prime of t, you'll just get negative sine of t squared plus cosine of t squared plus 1 squared, which just gets you sine squared t plus cosine squared t plus 1. Sine squared plus cosine squared t is just 1, so you just get the square root of 2. Okay, if we plug in the r of t to f, which is just x times y, you just get cosine of t sine of t. Okay, so now let's compute. We already know it's from 0 to pi over 2 cosine t sine t. I'm going to leave this outside. This will be dt. If we compute this, I'm going to do a u substitution where u is sine of t and du is cosine of t, which means this is out. So we get the integral of u du, and if we plug in a 0 to our original u, you get 0 because sine of 0 is 0, and sine of pi over 2 is 1. So this eventually integrates into u squared over 2 from 0 to 1, which gets us 1/2 minus 0, which is just 1/2. And then since we still have this square root of 2, you multiply it, which gets you square root of 2 over 2, which in this case is our answer choice B, which is correct. Hooray. Moving on. Okay, number 3. 5 of these 6 triple integrals are over the same region of space. This very weird tetrahedron here. So let's label our points. This is 0, 0, 0. This point out here is 1, 1, 0. This point up here is 0, 0, 1. This point here is 1, 0, 0. So one of these triple integrals is over a different region. Which one is different? Now, here's how you would solve this question. Work out in. So that means work from the outer boundary to the inner boundary. So in this case, how I'm going to do this is I'm actually just going to look through this, see what might look weird. None of these look wrong to me, so we got to work in. And if you stop at D, what you can see with D is that if we draw out what it's supposed to be, because you can imagine this as x in terms of D, so in terms of y. X in terms of y. So this is our x bound, this is our y bound. X has a point at 1, 0. There's already a point at 0, 0. Y has a point at 1, 1. So you can imagine this boundary right here, right? So since it's dx, it goes from left to right, which means that since this line is equal to y equals x, x equals y, and this is x equals 1, the boundary for dx should be from y to 1. But if we look at D, it goes from 0 to y, which is wrong, which is why D is our answer in this case, because D is integrating over a different region. So these questions are very weird, they're very big, but there are usually mistakes in there that you'll find. And in this case, like for example, if you're looking at this one, right, it's dy. And what makes it correct is because it goes from 0 here up to this line, which is x. So in these cases, you just have to look for one and just test out some points. Remember, work out in, and you'll find an answer. Okay, which vector corresponds to the one pictured here? Okay, you can think of these vectors as like, I don't want to say equations, I'm going to say half equations, right? Because what you have is you're going to be given a point that corresponds to a vector field. So what's a vector field? Well, let's say you have a point right here, right? Well, in this case, the vector field will be this. Since it goes to the left, your x vector will be negative, and if it goes to up, your y vector will be positive. So in fact, let's actually use this point right here, right? And test out a few things. Okay. So this is A. The vector for A is 1, negative y. So if we plug in a point here, we know that this point right here is a negative x and a positive y. So if we plug in a point as a negative x, positive y, this is already a positive 1. So already know that this cannot be the answer because it doesn't correspond with the vector. But what about this one? Well, this is a negative x, you plug in a negative, this is a negative x, you plug in a negative x, and you get a positive vector. So that can't be right either. Wait, sorry. I said that wrong. The vector is negative and it's positive, and since you plug in a negative point and get a positive vector, that can't be right because the vector should be negative. Okay, let's look at C. Okay, C has negative y and x. If we plug in our positive y point, you get a negative x vector, which is right. And if you put in the x, our x is a negative point, which means you get a negative vector, which is wrong. Okay, D. So D starts at 1. So since it's 1 is already a negative vector. So in this case, that's already wrong because 1 is a positive vector, which is wrong because our vector should be negative. So look at F. So F starts with y1. So if we plug in our y right here, our y is positive, but our x vector is negative, so it's wrong. And then with F, if you plug in a negative y, our y is positive, so negative y will become a negative vector, and 1 is already positive, so that's right. So in this case, the only correct answer for this vector could be F, since now we don't really know if this vector works because you'd have to test out every point, but we assume this vector works because all of these other vectors don't even work at this one point, which means that technically this vector probably works at all these other points. In fact, it definitely works at all these other points, but you'd have to test everything out. So that's how you get that. Okay, number 4. Find, oh my god, I'm not getting it. Okay, find this. Find the line integral f times the tangent vector ds, where the vector f x y z is equal to this very big vector on a smooth oriented curve. Okay, so now it's smooth oriented curve, which means that we can find a potential function. And it goes from this point to this point. So how I'm going to set this up is this actually tells me that I can use the fundamental theorem of line integrals, which states that this vector over here, f times the tangent vector, is actually equal to the potential function at point B, which is this one, minus the potential function at point A. So we got to find the potential function. So the steps for the potential function is, I want you to imagine this vector as component f, this is component g, this is component h. So you got to first integrate component f at dx, which gets us x, y, e, z plus some sort of constant. And then you got to take the derivative at y, which gets you x times e to the power of z plus g prime of yz. And then we have to equate this to g. Equate this to g right here, which gets us e times y plus x e to the power of x. These two cancel out, which means that g prime of yz is simply equal to e to the power of y. Okay, now that we have this, we integrate both sides with respect to y, so you get g of yz equals just ey. So now we know that our potential function will just be this plus e to the y plus a constant of h z, because there's a constant there. That's our current potential function. So now we gotta do step 3, which is taking the derivative at z. So this will become x, y, e, z plus, that'll be 0, plus a h prime of z. We equate this now to h, which is x, y, e to the power of z. So that h prime of z is equal to 0. So our potential function just ends right there. It just equals x times y times e to the power of z plus ey. And it'll also be plus to a constant, but in this case, we don't really need the constant. So now, we just got to plug in these points right here. So, the potential function at negative 1, 1, 1 will be equal to negative 1 times e to the power of 1 plus e to the power of 1. So you just get negative e plus e, which is 0. Now the potential function at 0, 0, 0 will be equal to 0 times e to the power of 0 plus e to the power of 0, which is simply equal to 1. And then if we do the potential function of negative 1, negative 1, negative 1, 1, 1, minus the potential function at 0, 0, 0, you simply get 0 minus 1, which gets you the answer negative 1, which in this case is answer choice B. Oh my god, I just skipped a bunch. Wait, I didn't put my smiley faces. Okay, remember 5 is D, and 4 is F. And 5 is B. Okay. Number 6. Choose the triple integral in spherical coordinates that represents the volume of a solid bounded by this cone lying between the planes z equals 1 and z equals 2. You don't need to compute the volume. Okay, so remember when you transfer to spherical coordinates, that dv that we have in rectangular becomes rho squared of sine phi d, oh my lord, I drew that weird, d rho, d phi, d theta. So we need that rho squared sine of theta. So we can actually eliminate some answers. Can't be B because it doesn't have that. Can't be C either. And it also can't be F. Boom, you just took out half your answer choices. Good job. Now, you can either look for rho or you can look for phi. In this case, I'm going to look for phi because I think it's a bit easier. I'm going to use this equation right here. Z squared equals x squared plus y squared. Now that z squared is equal to rho cosine of phi, means that, z is equal to rho cosine of phi, which means that z squared is equal to rho squared cosine squared of phi. Same applies to these ones. X squared is equal to rho sine of phi cosine of theta. So x squared will be rho squared sine squared cosine squared. And that's plus y, which is rho times sine of phi sine of theta. So y squared is rho squared sine squared, and also sine squared. So I can take this out. I can factor out a rho squared sine squared of phi, and it'll be cosine theta plus sine squared theta. This becomes 1. So now we know that rho squared cosine squared of phi is equal to rho squared sine squared of phi. Okay, so you can you can cancel out your rho's. In this case, cosine squared of phi is equal to sine squared of phi. Or you can just say that cosine phi is equal to sine phi. So what angles are equal, where in the unit circle are the angles equal to each other? That's right, pi over 4, where the point is square root of 2 over 2. So in this case, our phi is equal to pi over 4. So now we look at our answer choices, and which one of these is it it's 2 pi over 4. So in this one, it's actually all of these. I see that now. That's very funny. Okay. Okay, sorry. I had to pause the recording for a little bit because I had to go get my laundry. Okay, so we already know our phi is square root of 4, but in all these cases, that holds true. So now we have to find what our rho is. But we already know that z is equal to 1 and z is equal to 2. It's bound between these two. So since z is equal to rho cosine of phi, say that that's equal to 1, and rho cosine of phi is equal to 2. And what you can do here is you can just say that rho is equal to 1 over cosine of phi, and rho is equal to 2 over cosine of phi. Now, what is 1 over cosine of, phi or theta maybe? I don't know. Well, that's simply just secant. So in this case, phi is equal to secant phi, and this one is 2. Oh my lord. 2 secant phi. So if we look at our things, 2 secant phi, that's how you get the answer choice D, which in this case is correct. Sorry, I had to take a little breather to get my laundry, or else someone's gonna steal my laundry again. Okay, number 7. Find the absolute maximum value m and the absolute minimum value m of the function. So this is our f, and the constraint. So this is our g. So this is a Lagrange question, which means that we have to put it into the form gradient of f is equal to lambda gradient of g. So how do you do that? Well, we got to find the gradient of f, which in this case will just be 1, 1. The gradient of g, which in this case will be 2x minus y, comma, negative x plus 2y. So if we order this, we say that 1 is equal to lambda 2x minus y, because these two. And then 1 is also equal to lambda. I'm going to reorder this to be 2y minus x. So you can't do this every time, but for this time we can. I'm going to cancel these out by dividing them. Say that 1 is equal to 2x minus y over 2y minus x, which means that 2y minus x is equal to 2x minus y. In this case, 3x is equal to 3y if we move it over, which means that y is equal to x. So now we plug this back into our constraint. I'm just going to say that in this case, x squared minus x times x plus x squared is equal to 1. So this is x squared minus x squared plus x squared equals 1, which becomes x squared equals 1. So x is equal to plus or minus 1. So since x is equal to plus or minus 1 and y is equal to x, we now know that our critical points will be at -1, -1, because x is equal to -1, so y is equal to -1. And when x is equal to 1, y will be equal to 1. So now we take these two critical points and put them back into our function. So f of -1 will be equal to x plus y. So -1 plus -1 will get us -2. And then f of 1 will be 1 plus 1, which equals to 2. So we got to find m is equal to 2, while little m is equal to -2, which in this case is our answer choice A, which is correcto. Okay, number 8. So this is a cylinder question. This is a cylindrical question. In this case, we have this, so we can convert x squared plus y squared is r squared, but it's r squared to the power of 3 over 2, which is simply r squared times 3 over 2, which becomes r cubed. Remember, this dz dx dy becomes r dz dr d theta. So I'm going to put that right there. Okay, then after that, we know that based on this, x is equal to square root of 1 minus y squared. So x squared is equal to 1 minus y squared, which in this case means x squared plus y squared is equal to 1. So r squared is equal to 1, which means that r is equal to 1. So we already have our bounds. Since it starts at z, I'm going to keep it at z. I'm going to say from -1 to 1, then from 0 to 1, then it's a full cylinder. Oh, it also just has 1 right there. No, whatever. It goes from 0 to 2 over pi. And this will become r to the 4th dz dr d theta. So if you evaluate this from -1 to 1, you get r 4th dz, which gets you z d r to the 4th from -1 to 1, which becomes r to the 4th of 1 minus -1, which is simply 2 times r to the 4th. If you evaluate that from 0 to 1, 2 times r to the 4th, you get 2/5. That should be a dr right there. R to the 5th from 0 to 1, which is simply 2 over 5. And the last step is evaluating from 0 to 2 pi of 2/5 d theta, which simply gets you 2 over 5 times 2 pi, which gets you 4 pi over 5. So in this case, it's answer choice C, which is the correct answer for number 8. Okay. Number 9. Hint, polar. So we got this double integral right here, and they want us to use polar. So we're going to use polar. So x squared plus y squared, we already know, is equal to r squared. Dx dy becomes r dr d theta. So times r dr d theta. And then since we know that this case x is equal to square root of pi minus y squared, we can just oversimplify this and say x squared plus y squared is equal to pi. It means that r squared is equal to pi, which means that r is equal to square root of pi. And now, if we want to find our other bounds, we got to look over here, right? So we know that in this case, x has to be greater than 0, and y has to be greater than 0. So what this means is that while y can go to pi, x can only make it so far to pi over 2. So we got to stick with x in this case. So our bounds will be from 0 to pi over 2, and from 0 to square root of pi. And that'll be sine of r squared times r dr d theta. So if you evaluate from 0 to square root of pi, sine of r squared times r, I'm going to use u substitution, say that u is equal to r squared, so du is equal to 2r. In this case, we get rid of this, get left with 1/2 sine of u, and we're going to evaluate this. If you plug in a 0 to r squared, you get 0. But if you plug in a square root of pi to r squared, you just get pi. So this becomes negative 1/2 of cosine u from 0 to pi. Then take the cosine out. Sorry, 1/2 out. It'll be cosine of pi minus cosine of 0, which is simply negative 1/2 times -1 minus 1. So you'll just get negative 1/2 times -2, which is just 1. Okay, now we just evaluate from 0 to pi over 2 of 1, which simply gets you the answer pi over 2, which I believe is the correct answer. Yep, F for number 9. Okay, number 10. Change this order of integration for the double integral dy dx. So y runs from the parabola y equals x squared, while as the lower bound, and then it goes to y equals 2x as the upper bound. So as you can see, runs from here to here. Now we want it to change to run from here to there. So we got to change these. So if y is equal to x squared, we can just say that x is equal to the square root of y. And if y equals 2x, you can just say that x is equal to, well, x is equal to y over 2. And we know that y over 2 is going to be our left bound, while square root of y will be our right bound. So we got to look for answers that have that. Well, I guess in this case you can say left is bottom and right is top. So, nope, can't be A, can't be B either, can't be C. I don't even know what's going on with C. It can be D, and it can't be E. So now we have to evaluate our dy's now. So how do we do that? Well, now we know that our bounds go from y over 2 to square root of y, which means that in this case, y over 2 is also just equal to square root of y. Why? Well, because there's the less than or equal to signs right there. Emphasis on the equal to. So if we square both sides, you get y squared over 4, which is equal to just y. And we can change this to y squared over y, or equals 4. So we just know that y is equal to 4. So which one has a 4? Right here, which means that answer choice F is correct for number 10, which is the correct answer. Okay, number 11. Given the force field, this vector F, y, dx, find the work required to move an object along the straight line segment from 0, 0, 0 to 2, 3, 4. So we gotta parameterize a line segment, which is simply the start point plus t times the vector of finish minus start. What is finish minus start? This is our finishing point, this is our starting point. So the finishing point size start is simply 2 minus 0, 3 minus 0, and 4 minus 0, which gets you 2, 3, and 4. That should be a vector times t. Our start points are all just zeros, so simply, in this case, when we parameterize, our r of t will just become 2t, 3t, 4t. And our r prime of t becomes 2, 3, and 4. Now, remember, since our f is a vector, r is a vector, the form for this one will simply be the f vector plus t times the r dotted, the r prime of t. Not the magnitude of r prime of t, just the r prime of t. So now we know our r prime of t is 2, 3, 4. If we plug in the f prime of t, if we plug in the r of t to the f, we simply get it's y, so that's 3t, d, 4t, and x, which is 2t. So now f times r prime of t will be equal to 6t plus 12t plus 8t, which gets you the answer 26t. And then if we integrate from 0 to 1, which is same with all line segments, you get 26t dt, which gets you the answer 26t squared over 2, which is 13t squared from 0 to 1. Simply gets you the answer 13, which is answer choice A, which is the correct answer choice. Okay, now, last question. Use Green's theorem to evaluate this integral, x times dx plus x plus y squared, x squared plus y squared dy, where c is the boundary of the rectangle with these vertices. So Green's theorem simply states that if this here is f, this here is g, then Green's theorem is the double integral of the region D of the partial derivative dg with respect to x minus df with respect to y. And in this case, since they're all just xy points, I'm just going to say dx dy. So what is dg? Well, in this case, it's just 2x, and f does not have a y, so it'll just be 0. So we're just going to integrate 2x dx dy in our bounds, x goes from 0 to 2. Y goes from 0 to 3. So now we've set up our Green's theorem. Let's do this. So from 0 to 2 of 2x dx dy, you simply get x squared from 0 to 2, which gets you 4 minus 0, which is just 4. And then from 0 to 3 of 4 dy, you get 4y from 0 to 3, which gets you the answer choice 12, which is answer C, which in this case is correct. Now, this may be the last practice exam I do for this exam. Maybe not. But our exam is coming up super soon. So I hope you've learned some good stuff. I hope you learn good math. Hope you practice, and wishing you the best on the test. And have a good day.